Hello, folks. Welcome to Rational Science, the only site on the internet that does physics rationally. Everybody else does what? Mathemagics. That's what it's called, mathemagics. They move concepts around. They move the mass. They carry the mass. They transfer the energy and they shake the field, and they think they're moving objects. It's all math. That's all it is. They have no explanation of how this universe works. Okay, we're going to be doing a little bit of space-time today, a little review of special relativity. And while we're at it, we're also going to be doing the subject matter of today, which is gravity. Okay, and then we're going to have some questions at the end as well that we're going to answer from people who asked them during the week. Actually, from 2 weeks ago. We didn't have time last time, so we're going to cover that. And we're going to start out with our extinction segment. And hello. And then we're going to look at some of the headlines that are happening today, and how they affect, how they're related to extinction. Again, we don't do politics here, really. We try not to. I mean, sometimes we might, not really intentionally. What we want to do is relate the headlines and some of the news that's out there to extinction, how it relates to extinction. And again, what we're saying is that extinction is an issue of ecological pyramid overturn. Okay, the ecological pyramid is going to overturn on us, and there is absolutely nothing we can do about it. Okay, we might be able to postpone it a little or shorten it a little, the postpone it or make it come sooner, but other than that, we cannot avoid it altogether. Okay, so let's get going with our extinction segment. Here we have one bit of news. It says China renews embrace of Maduro's Venezuela as the U.S. looks on. Okay, and so what is it? Venezuela and China are reestablishing connections after years of cooling ties, with government contacts resuming and joint projects floated in what amounts to a challenge to Washington. Now, what I put up there is 2016, a map that shows all the bases that the United States has around China. That was in 2016, and a lot of these are renewed. Others, are new ones that have been put in place since then. And it says that at the bottom, today more than 400, and that's 2016, right? More than 400 American military bases encircle China with missiles, bombers, warships, and nuclear weapons. Okay? But on the other hand, imagine now that China were to do something similar. It starts, having relations again with Venezuela, that red country there at the north of South America. It already has relations with Cuba. They share common ideology, communism, right? A political ideology. And then you have Nicaragua, which more or less is in the same boat. And they have good relations with these three countries. They could start new relations with other countries that might depend more and more on China. For example, Brazil, the big country there, its number one trading partner is now no longer the United States, but China. And so just imagine that. And I've been to Argentina, and let me tell you, lots of Chinese over there lately. And so imagine that goes beyond just the commercial aspect, and they start putting their aircraft carriers, as you see there, around the Caribbean, maybe even in Mexico. Remember, Mexico has a little bit of a gripe against the United States. Might want to recover the territory from Texas to California. And the fact that, that was taken away by President Polk in the 1840s. And you might think that maybe the Mexicans have already taken over. There's more Mexicans there than standard Americans, right? All that southern part of the United States. I know because I live there. And so just imagine that Mexico were to have relations with China to a point, not just commercial, relations. But military, they decide to do joint exercises, as they're called, around the United States. What do you think the United States would do? Would the United States be happy with that? Uh, so that's more or less the situation over there in China. Just think about that. They're all mafias. I look at them as all mafias. So one mafia say, "Hey, you're in my backyard. I don't like you over here, with all your weapons and, your machine guns and bombs and hand grenades." And the others say, well, we're taking democracy. We're protecting all these countries, okay. So there's always excuses to surround a country. And just wonder a little bit what would happen if it's in reverse. Imagine what happened in, what was it, 61 with Khrushchev sending more than just standard missiles, but ICBMs into Cuba. The United States didn't like that at all. And so that's more or less the situation. All these mafias, they try to see what they can get away with. And so that's where the world is. Okay, here's another piece of news, and it's a little contradictory because on the one hand, same day, by the way, May the 3rd, okay, and in one headline says, U.S. envoy to China says next steps to improve relations are up to Beijing. And the envoy, he says, we need better channels between the two governments and deeper channels, and we are ready to talk, Burns said, speaking to the okay? And we've never been shy of talking. We hope the Chinese will meet us halfway. We don't want a conflict with China. We don't want to return to the Cold War with China, and we need greater stability in this relationship. Same day, the news comes out, says, U.S. senators launch a renewed push to thwart China. Talk about, oxymorons there, double talk. Yeah, on the one hand, they want to improve ties, and the other, Congress saying, we're gonna create problems for China, as many as we can. Yeah, there is a war going on already. There is a Cold War, so to speak, going on. And the question is whether that's going to lead to a hot war. Okay? In other matters, here we have India, apparently has surpassed China as the most populous nation, not because they counted everybody, but because they project the rates, the growth rates, and so on, And it says China's population is likely to begin shrinking next year. So China's coming down, but India is still going up. But it says India's fertility rate has also fallen substantially in recent decades, from 5.7 births per woman in 1950 to 2 births per woman today. And here you can see the chart, okay? You can see what's happening to India's population in the last 60, 70 years maybe, okay? It's come down. And so both countries, not only China but India, their rates are coming down, okay? But it says the following, it says the UN expects the population to peak around 2064 and then decline gradually. That's for India, right? India having more people than China is no longer significant in a concerning way. What do you mean by that? Well, it says rising incomes and improved access to health and education have helped Indian women have fewer children than before, effectively flattening the growth curve. Okay, so they think that's positive. Okay, because they're not producing children. Instead, they're producing something for the economy, and their incomes are rising. Their health and education are becoming, more modern. Then there's migration. And listen to this, some 200 million Indians have migrated within the country between states and districts, and their numbers are bound to grow. Most are workers who leave villages for cities to find work. Yeah, it's known as urbanization. It's happening throughout the planet. Okay, everybody on the planet every country is having this urbanization movement, pretty much. And our cities will grow as migration increases because of lack of jobs and low wages in the villages. Okay, so what's happening? What's the cause of women not having children, not having, why the birth rate is dropping every country on the planet? It's got to do with urbanization. That is the underlying cause. And yeah, when you move to the city, well, you got different education. You've got different, especially economic situation, right? Maybe you can't afford 10 children anymore like you did in the country. Okay? So these are the situations. But I think the bottom line is that as you move to the city, you stop having children. There's no room for children in the cities. And the same thing is happening in the U.S. Here's the U.S., okay? More U.S. women are avoiding unwanted and mistimed pregnancies. Births and pregnancies in the U.S. have been on a long-term decline. A new data analysis provides one reason. It's becoming less common for women to get pregnant when they don't want to be. Okay, it sounds like they used to do, forced sex in the past. Is that what they mean by this? And they don't want to be now? Okay, what happened before? The data indicates that far fewer individuals were becoming pregnant in 2015 than in 2009, and that abortion incidence went down because individuals do not get pregnant, not because their pregnancies continue to a birth instead of an abortion. There's also data showing that young people are having less sex, perhaps because they are socializing online more and engaging in fewer risky behaviors overall. And yeah, then there's the issue of economics, especially if the kid stays at home. There's a very little chance of them forming a family, and they don't care about that anymore. They probably have some casual sex out there, then come back home, and they're not going to have kids inside their own home, their parents' home. Fertility rate has been increasing among the oldest childbearing women. So women are having babies later on in life, 35 to 44. They run into fertility troubles at older ages. So I think not only are they having them later, but the kids are not coming out right. I think that's happening as well. Okay, but a lot of them need help of all sorts. Um, Maybe there's more cesareans. And this is the trend. Look at the trend. Scary, yeah? Look, this is since the 1800s. Do you think the rate has come down? And where's it headed? Well, further down. Certainly not going up. The United States is making up for all that with immigration. So the United States is allowing all European countries as well, by the way, Western European countries especially, they're allowing immigration. And because, immigration is kind of replacing the lack of kids, that fertility, in other words, right? That's not happening. And so keep that in mind. But fertility is dropping in countries like Nigeria, which used to have much higher rate of children production. Now all those people are moving to the cities again, to the big cities, and they're not having children. And what few children they do have are coming to Europe and the United States, from India, from China, from different places, from all of Africa. Okay, we discussed this last time with my son. It's got to do with AIs. Okay, one fellow who worked in the industry now quit so he can speak his mind. And they say artificial intelligence pioneer leaves Google and warns about technology's future. And I've got a problem with what he says because on the one hand, he says that there's a problem with bad actors using it for bad things. Okay, that's one concern about the warning for the future. And then on the other side, the idea that this stuff could actually get smarter than people, a few people believed that. And now he does believe it, and it's going to happen sooner than later. Well, we got a problem. What is the issue with AIs? Is it that someone might use the AI for bad things, or is it that the AI is going to get smarter than people and will not need a bad actor to direct them to, rule over him? So we have two situations here, and these people do not, really reconcile these two different versions. Are we concerned about bad actors using AIs, or are we worried about AIs taking over the world because they get smarter than people? And meanwhile, this fellow says that what the AIs are being used for is to replace people in what? In healthcare, climate, education, engineering. And yeah, if anything, they're going to be pushing people out of work. That's, again, maybe the last stage of efficiency in an economy where they bring these AIs that do a lot of work that humans don't do either as well or whatever. The AI does it more efficiently. For sure, you don't have to pay him a salary. So in that sense, it's more efficient. It's more cost effective. So it might happen that AIs replace humans in many parts of the economy. When, not the if, but when that happens, all we're just doing is creating more unemployment, if anything. Where are we going to put people to work? Are they going to just stay at home and receive a paycheck from the government? Is that the way it works in a future society? So keep all this in mind. AIs, if anything, make everything more efficient, and that's not good. The more efficient we become, the less work there is. Especially if there's no one to buy the product because they're on welfare or whatever, or unemployment, and so they don't have as much disposable income to go out there and buy, especially expensive goods. And because of that, they don't sell as many. The big companies that produce these goods compete against each other. They kind of merge or go out of business or whatever, and that's more unemployment and so on. And so, yeah, AI is not good news for the economy at all, okay, if anything. But for them taking over humans, that's, as far as I'm concerned, that's Hollywood stuff. It's got nothing to do with reality. It'll never happen. And here's a fellow says regarding some of my extinction theories, and he says he doesn't accept that it's going to happen through food or through the ecological pyramid overturn. He says, I don't think reconstructing past extinctions, which is what I suggested the other day. I said we should do 101, Extinction 101 before we do Extinction 102. Extinction 101, mass extinction or just extinction. You can do background or mass, whichever one you want. But you have to explain mass extinction. You got to say, look, this is how extinction occurred in the past with the animals and plants that have disappeared. Please explain that first. Then you show that you know something about extinction. And everybody wants to brush that off, this fellow also. He says, well, I'm not going to do that because it's not relevant to humans, okay? And so he says, what's going to happen? Well, modern ecological conditions rearrange the natural order. Talks about natural order and talk about ecology. So the guy is looking at the environment, not only your surroundings, but also the food, the diseases, these kinds of things. That's what he's got going through his mind, right? A lot of people think like him. Biosphere collapse, that's what he's got in his mind. He's got addictions, shooting up, etc. Hedonism, profit motive, all these big corporations just taking advantage of us poor little people. They sell us all this garbage that we don't need, and that's bad for the environment essentially, right? Because we have all this nonsense that we don't need. Infertility, okay? And then we have poison air, poison water, poison everything. Everything's poison. They sell us all this poison that we have to eat because there's nothing else to eat in the cities especially, right? And so a lot of people think like him. They think there's this great conspiracy up there, the New World Order folk, the Illuminati, and what they do is, they have all these things up there that they're shoving down our throats. And it's changing the environment, and that's what's going to kill us. Well, the problem here is that, when he says the ecological collapse, okay, or whatever, you can't just say the ecology collapses. You got to show me a mechanism. You haven't explained the mechanism how all this kills us. Okay, how does this produce the extinction of humans? None of this. This is just a shopping list of gripes. I don't like the government. I don't like the modern society because look at all the stuff that we got out there. We have prostitutes in one place. We have all these drugs in the other place. It's a mess out there. Yeah, none of that explains extinction. Okay, so please explain the mechanism of extinction. Don't just say ecological collapse because that doesn't tell us anything. Okay, you got to have a mechanism. And again, that's why he avoids past extinctions because he cannot explain them. He would not be able to explain how the dinosaurs disappeared or, the Permian animals, Triassic, and so on. He would not be able to explain that. And so he wants to skip that and say, no, let's go to humans because we're unlike all the other animals. We're not animals. That's more or less their way of thinking. Yes, we are animals. We belong to the world called mammals. But people think that because we have a higher level of intelligence than all other species out there, that somehow God designated us the keeper of the garden. We're the gardeners of Eden, main gardeners, the guy in charge. We're not. We're just another little animal in the kingdom, okay, in Eden. And people don't understand that. They say, no, no, we rule the planet. Yeah, so did the Triceratops. I'm sorry, the T-Rexes in their day. They ruled the planet, and they're gone. Didn't help them any, the fact that they were the top predator, apex predator, right? Okay, another fellow says the following. He says, there are too many people for food shortages to cause extinction. Africa is a great example. Feed Africa and the population explodes until the infrastructure can't take it. Okay? Then a massive famine. Okay? Then a few years later, the population is exploding again because the food is being shipped in again. So they stopped shipping food in there. Why? Because of money, or what's the issue? If nothing else, those who are willing to eat people will have a readily available food supply until population matches carrying capacity of the land being inhabited. Long on Soylent Green. And for those of you who are not familiar, Soylent Green was a movie that they had where they used people, at the factory. They put the people inside the machine, and that's where the food came out of. The food that they sold the people who were living. Okay, so and it says there, and this is in the Wikipedia, just the first sentence, right? It says by 2022, which is 1 year ago, right? The cumulative effect, this was a 70s movie, by the way, the cumulative effects of overpopulation and pollution have caused severe worldwide shortages of food, water, and housing. So I just want to make sure that we understand that that is not the theory that we propose at all. This is not a question of shortages, which is what this fellow thinks, that it's a question of, being close to the carrying capacity. When you exceed it, right, density dependent birth rates, right, kind of thing, there's going to be deaths. And what happens is that brings the population back down. Now it's back to carrying capacity. We're okay. We're a little too low. We start producing children again. That's what they have in the back of their minds, that there's this seesaw going up and down. That's not the case. Not the case at all. That's not our theory, by the way. What we're saying is the global economy is going to collapse. It will collapse. There's no doubt about it. It will collapse because we cannot grow forever economically. Okay? We cannot grow forever, partly because population doesn't grow forever, and our global economy, human economy, is based on the fact that, or on the expectation that in the future there's going to be more people, more consumers, and we're going to have more demand. And so companies say, okay, we're going to expand because there's going to be more demand. If population starts coming down or levels off or whatever, then these corporations are going to have a problem because they will not be able to, through quality, replace quantity, okay, which is essentially, what demand is. You need to sell more and more goods and services. And what's going to happen is if population comes down and people maybe stay at home, they don't need as many services because they're just going to stay with mom and dad, or maybe they get married and don't have kids, they have a place to stay. They don't need to keep buying and buying and buying forever. And especially if they don't have kids, there is no new consumer base. If that doesn't happen, the economy will definitely collapse. So what you got to look at is the projections. Think of it this first in long terms. That helps you reason it out. Are humans going to live 1,000,000 years, a million more years? And the question is population going to increase in the next 1,000,000 years? How is it going to increase exponentially, arithmetically? How is it going to increase for the next 1,000,000 years? Okay, that's the first question you have to answer, or at least a factor that you should keep in mind. So if you think that population is just going to kind of stop growing, we're going to reach some kind of plateau, and it's just going to go up and down, more or less in a constant population overall. Well, you have to justify that because that's not happening. What's happening is the population of the world is becoming older. Of the world. Population of the world, of the entire planet, is a human population, right? Is becoming older. Okay? That's one of the reasons we're having fewer kids. The other one being, we're moving to the cities, urbanization. And if we have fewer kids, what you have is the overturning of the population pyramid of humans globally in general. Some countries will have a little more younger people and they'll have more kids, but especially the advanced nations, they're not going to have kids, because people are already settled. They're stabilized, and the only way they're going to get people is through immigration. And so the question is, at some point, population is going to stop growing, especially as it used to in the 19th century, where it went exponentially upwards. That's going to stop. It's already stopped, in fact. And now it's leveling off, and what's going to happen is you got a double whammy. On the one hand, you don't have consumers, and on the other, you're getting unemployment because you don't have consumers. Companies close because they can't sell their products evermore, right? And at some point, there is a crisis, and you have a collapse of the global economy. You can't just create money out of nowhere and say, oh, we're just going to give it to you and you stay at home, because the AI took over your job or whatever. Okay, so the issue here is that if you're going to say that humans are going to live another million years, boy, you got a lot to justify. And if you say, well, a million years, I don't know what's going to happen in a million years. I don't care because I'm going to die before that. Okay, that's true. But then you got to have an idea of whether we're going to live another 1,000 years, another 100 years, another 10 years. I mean, if I get down to 10 years, will you react and say, well, no, we're not going to die in 10 years? Well, explain why. Why not? I mean, maybe the global economy collapses before the next 10 years, and then what? What do we say? So if you say no, please justify it. Okay, that's the way it works. Okay, let's move on to I'm going to do a little review of special relativity, which we did last time. Okay, we've been doing it for the last couple of weeks. Okay, we talked about the fact that we have length contraction and mass increase and time dilation, all that good stuff from special relativity. Is any of that stuff from special relativity? Does that have anything to do with science? Does that have anything at all to do with physics? Let's find out. Yeah, here's I'll start with my universal movie. Okay, and the universal movie again is a tool that I use. I recommend it to everybody. And what it is snapshots. You had these motion pictures, especially when you had in the 1920s and so on. One frame at a time, went through the lens, and so if you just looked at one frame, well, there's nothing moving inside the frame. If you want to see something moving, motion picture, well, you had to have the whole reel go through the lens, right, so that it's shown on the screen. And so the question is, when you look at a single frame of the film, nothing is moving in there. That's more or less what we're talking about when we say the universal movie. We're going to treat it as a movie. You can call it a three-dimensional movie. You can say it's God's movie. Okay, so God has filmed the movie. Now he's got the film there, a three-dimensional film, and so he's got all this. You look at any given frame, and everything is just static. Nothing is moving. He just took pictures, of what was happening in the universe. And what you see in one frame is just all the atoms just in one location. You'll see all the planets in one location. You'll see that every star and galaxy, everything is a given location. Okay, nothing's moving in that frame. And in order to see something moving, you have to go to at least two frames. Okay, so we have the universal movie, single frame, nothing is moving, and within that you have only static concepts. You have all the objects, you have location, you have distance, existence. That's all in a single frame. You don't need motion for any of those concepts. On the other hand, if you want to have, motion, you want to have time, well, you got to go at least to two frames. In other words, you have to have the film rolling along, okay? And that's more or less the notion behind the universal movie. And here you see it, okay? Here's the frames of the film. You have the static concepts at the top and the dynamic ones at the bottom. You can see the ones on the top, the yellow region there, it only points to a single frame. The beige one at the bottom points to at least 2 frames, and you can put more if you want, but at least 2 frames is the minimum to create all these dynamic concepts such as motion and time and energy and so on. Okay, why is length and mass, which is what we've been covering, why are those static concepts? Well, we look at the definitions, and here are the definitions of physics. Okay, what is length? Continuous matter between two surfaces. What is mass? Number of atoms. Okay, quantity of material, matter. That's what mass is. And I just want to point out that not only time is a dynamic concept, which is down there at the bottom right, okay, which is time dilation. So you can't put it in there with length and mass, but you've got inertia. And I just want you to keep in mind inertia, which is resistance to motion. Okay, in other words, a force comes against you and you push in the opposite direction to that force. That's called inertia. It's a resistance to change, right? And so inertia is a dynamic concept. Inertia is not a synonym of mass because mass is quantity of matter. Okay, so keep that in mind. Okay, we have a contradiction because they define mass as inertia, and no, they are two different things. If you're going to talk about inertia, inertia you can say almost is the opposite of weight. Okay, because you have something weighing down or sideways, right, and or pushing in a given direction, right, and something that opposes it, which is could be the atoms that make up the thing that you're weighing, right, or it could be something that is preventing that thing from moving. Like, you can put a box on a table, and the inertia of that is zero, really, because it's not moving at all. Okay, unless a force acts upon it, right? So just keep that in mind. Mass, did it lose its mass? Is mass zero because inertia is zero? Okay, keep that in mind. Okay, so here we have good old Stevie Hawking. Okay, he died a few years ago, and he wrote in his Brief History of Time. You'll find this in the glossary. Okay, mass, the quantity of matter in a body, its inertia, or resistance to acceleration. Well, quantity of matter, like if you have 10 marbles in a bag, there's only 10 marbles in there. That's quantity of matter. If you look at every marble as, a piece of matter, as a unit of matter. So you got 10 marbles in there. Do we need to know? Do we need to measure? Do we need to count them? No, we don't. Mother Nature knows there's only 10 in that bag. Before you count them, before you measure, before you do anything, there's already 10 in that bag. You can later on count them and say, oh, I counted them and found out that there's 10. Mother Nature already knew that. God already knew that. The devil already knew that. All these guys up there whom we pray to every day, they already knew how many marbles are. It's a fact. It's a question of existence. There exists 10 marbles in there, whether you count them or not. Okay? This is not a Schrodinger cat kind of thing where the cat is dead and alive at the same time. No, God knows whether the cat is dead or alive before you look. Okay, so just keep that in mind. One thing is existence and what is, and the other one is measurement of what you perceive or what you measured or what you understood. Maybe you're drunk and you don't even know what you're looking at, so it doesn't matter what you concluded. What matters is what is, independent of your conclusion. And so here we have mass, quantity of matter, a contradiction because quantity of matter does not match inertia, which is resistance to acceleration. Okay, weight, the force exerted on a body by a gravitational field. It is proportional to, but not the same. It's its mass. Right, of course, because weight is inertia, or you could say it's the opposite of inertia. Weight is what goes down, and inertia is what tries to prevent weight from going down. So it's kind of like an antonym of weight. That's what inertia is. Okay, so yeah, if you try to cover all the bases like Hawking did there, and here you have a PhD, many years in the industry, theoretical physicist, mathematician, right? Yeah, you don't define terms precisely. Why? Because you can get away with murder. If you define that word in two different ways and you say, look, it's a quantity of matter and it's also inertia. Well, which is it? I mean, those two are not synonyms. Quantity of matter is not inertia. Okay. Okay. Here we have situation. The fellow says the following says, well, this was from Quora, okay, and I like what this person said, so I thought I'd put this up there. Many people think inertia is mass. Others think it is momentum, depends on the object's mass and speed, while others think it is a force. This guy says he's a physicist, okay? It is not a quantity, inertia, right? Even the vague idea is not well defined in physics. Absolutely. They don't define these terms because if they did, they would be in sorry shape. It is best to not add to the confusion. Don't use the word. There is absolutely no need for it. There is no bit of physics which requires the use of inertia. In most cases, a better word like mass does the job. Okay? And yeah, there you have mass, has 1 trillion hydrogen atoms. That's what that box has. And its inertia, I guess, is 0 because it's not moving anywhere. Okay, so what is its inertia? So yeah, you can't say mass is inertia. Absolutely not, because inertia is really related to motion, whereas mass is not. Mass is quantity of matter. And if you want to define it otherwise, then you can't define it as quantity of matter, and we have a contradiction. What are we going to call quantity of matter then? You know, when we say that we take the grand kilo from France, you know, the one that used to be the standard for mass, and we take it to the moon, it weighs less. And people say, well, its weight changed, but not its mass. And so what are we referring to when we say that its mass did not change? Well, we're saying its quantity of matter did not change. What changes its attraction to the center of the object, the celestial object. That's what changed. But the mass did not change. What do they mean by that? Quantity of matter. So then don't say what's its inertia. No, inertia is weight in a different, it's a different way of rephrasing weight. That's all it is. It's the opposite of weight, so to speak, like an antonym. Okay, so what are the conclusions that we have from special relativity from the last couple of weeks? A prediction is not a theory, okay? And we had that with our science critic, and we finished with him because there's nothing more to address. I think we addressed every issue that he raised, okay? So we're not going to have this fellow on here, at least not for now. A prediction is just a description. You know, if you say that something's going to happen tomorrow, so far you haven't told us why. You haven't given us an explanation, a cause or a mechanism. Oh, you said it's going to happen, okay? You said, my horse is going to win tomorrow at the race. That's a prediction, okay? You haven't explained why he's going to win, okay? An explanation is a theory, okay? So remember, if you explain something, now we have a theory. The theory of special relativity, SR, right, is not a theory, but a description, okay? It's not, there's no explanation in special relativity, okay? Special relativity predicts that an object traveling at near sea will shorten in the direction of travel, gain weight, and waste your time. That's what special relativity is in a nutshell. SR, you know, special relativity, does not explain the physical mechanism underlying these events, these phenomena. Okay, they don't explain that. They just say it's going to happen. We measured it. Here are the numbers. Okay, you told us that it's going to shrink, but you haven't told us why. What physically is happening in there? That's what we need. That's an explanation. That's a theory. Okay. And it says the icing on the cake is that special relativity denies that these phenomena are real. Why? Because they say that in your proper location, right? Proper length, proper mass, proper time, you know, that's the one the guy's carrying with him. The watch that you're carrying, that's proper time. The ruler you're carrying, that's proper length. And the mass, you know, whatever, the grand kilo that's close to you, that's got a given mass. So what is it about? It's about the guy far away who's measuring all this stuff. So it's about measurement, not about what is. Okay? What is proper. And proper has not changed, they say. So if it has not changed, who cares? You could be drunk for all I care, measuring from afar, and that changes nothing. Existence has nothing to do with special relativity. Cleans its nose holes with it, because special relativity says from afar we're going to measure, and we're going to measure differently than the guy who is close to the object, okay? Which is called the proper length, proper mass, proper time. And so if for him the time doesn't change, then that's the real time. That's the one Mother Nature blesses, not what the guy measured out there. You know, we don't care what he measured. Okay, that's what special relativity is about. And again, if they say it's real, which they don't, because they say in its proper frame of reference, nothing changed. Okay, so they do concede that, so nothing changed. And it's a question of measurement. Who cares about that? If you measured wrong, or you measured something with the wrong device, who cares? Measurement means that you're wrong. You just got to correct the device you use to measure. That's all it means. So, yeah, it says special relativity is strictly an issue of measurement, and therefore no concern whatsoever to physics or science. Okay, it's an issue of measurement, and we don't care about that. That's some concerns the mathematicians. You know, they want to play around with the fact that something measured differently. Okay, fine. Joey measured one thing, Johnny measures something else. Who cares? You know, who is correct? Well, correct is the guy who matches Mother Nature. Okay, if there's 10 marbles in the bag, and that's a unit of measure, we have 10. And the guy can travel at the speed of light. He can go do whatever he wants. There's still going to be 10 in there. Okay, and nothing's going to change. Okay, and so don't tell me that the mass increased, that now we have more marbles because you traveled at the speed of light. I'd like to have whatever he had. I want to travel at the speed of light too. Okay, so here we have some authority. Okay, Fermilab. We have Don Lincoln. He's a fellow who does physics. You know, physics, mathematics. That's what he does. He just tries to explain what the mathematicians do, or what they believe in, what this religion is all about. Okay, and here it is. And yeah, he's a caricature of a physicist, and he says relativity has been thoroughly tested, and there is no credible criticism of the theory. And he's so gullible, you know. He just accepts all this stuff at face value. You know, it's just like he just memorized it in school or something. You know, and he just spits it out. Okay, so. You know, they just say, look, it's a fact. We've proven it. Well, this is what we believe in. And we believe the ruler shortened in one direction, gained weight, and time was wasted. That's what they come down to. But he does say one thing, which is a historical thing. Okay, here it is. He says, relativity key concept, Lorentz gamma. Right. Okay, so the Lorentz gamma is the key concept in special relativity, and I went over that a couple weeks ago, somewhat not very important for science or physics. That's why we don't dwell on that nonsense. It's an equation. That's what it is. And the question here that I'm going to raise is not that it has any validity or any importance, really. Validity, we don't care, but it has no importance in science or physics, okay? It's got to do with mathematics, with them using that to say, oh, length contracted, mass increased, time dilated, okay? What I want to show is that it wasn't Einstein, who came up with any of that, okay? And here you have a little bit of history in a chart, okay? How this equation, which you see it there, Lorentz factor, okay, that's the gamma that they were talking about, that Fermilab was talking about. In 1887, we have Michelson and Morley, and what they did was they ran a series of experiments. This was, I guess, the most important one, where they wrote their paper, and they said, look, there's no ether. Everybody believed until then that there's all these particles out there filling the vacuum space, right? And that the movement of these particles is what light is, the vibration of these particles, okay? And about a year later, all these people, Heaviside, Fitzgerald, and Lawrence, all these people believed in the ether, and they were a little upset that at the results. And so they tried to explain the Michelson-Morley experiment, and they said, look, let's not abandon the ether. We just have to explain it. Okay, and so Heaviside, he had worked with what he called charges, electrons, and he wrote a paper where he said, look, in the direction of travel, the electron flattens out. So that was the length contraction. And Fitzgerald heard about that. He said, oh, we can apply that to light as well. So maybe the photon of light, or whatever light is, maybe the wave, flattens out in the direction of travel. And so he wrote first to a magazine, I think to Science magazine, or one of those important ones. And then he wrote a paper. By the time you get 3 years later to Lorentz, he comes in there and he comes up with this Lorentz factor, which again, the crucial factor is that 1 minus v squared over c squared, velocity of the object over velocity of light, right? Squared. And this had already been coming through, there were lots of mathematicians that had already worked with that relation. But today we give credit to Lorentz, okay, and say, okay, he came up with the gamma factor, and this is the one they're going to use to multiply and divide and to show that time dilates and mass increases and length contracts. And one of the guys who did a lot of that work was Poincaré. He was a French guy. And you can see how old Einstein was in all those years. He was 8 years old in the days of Michelson-Morley, 9 years old when Heaviside wrote his paper, his paper really, because he did write a paper. And Fitzgerald, he was 10 years old when Fitzgerald proposes it to explain the ether. Lorentz, Einstein was, 13 years old? And then finally, he took the credit for discovering special relativity. Nobody knows any of these other guys. Everybody just knows Einstein. Okay, he's given the credit for all of it today. And I just want to point out that, that is not the case. In fact, here, you'll look it up in the Wikipedia. Okay, this is a list of all the people who worked, all the mathematicians, right, that worked on the Lorentz factor. Okay, and there's a few of them there, okay? So you can look this up, okay? It's all those people who contributed to the notion of this Lorentz factor until they finally zeroed in 1892 on this gamma factor, which is what they use to explain the measurements, right? That's how it works. Okay, they still haven't explained the physical cause, okay, and that's why it's not a theory. All they're saying is, look, if you put this factor in there, that's what it'll do to the equation. Okay, that explains the equation. It doesn't explain what happened to the object, why it increased in mass, why it time dilated, and why length contracted. Okay, what we want to know is the physical mechanism that causes an object to do all these things when it travels close to the speed of light. That explanation, that theory is not, you'll never find it in special relativity. Okay, there's no explanation. Okay, and what's interesting about all that is that Einstein, even today, is credited with having gotten rid of the ether. They say that's what was different. That's what his contribution was to length contraction and the Lorentz factor and all this stuff, special relativity. His stuff was getting rid of the ether. Not true. Okay, here's Einstein, 1920, and we're talking 1908 is when special relativity is given birth. You could say even 1905 with the mass paper that Einstein wrote. Okay, that's another way of looking at it. You can also look at it from Poincaré's work, which preceded Einstein's, okay? And this is what Einstein says in 1920, several years later. He says, we may say that according to the general theory of relativity, and remember, special relativity is a special case of general relativity where there is no gravity. It's flat land, essentially. You can't fall down in flat land. That's special relativity. What they've done is taken away gravity. But it's a special case of general relativity. That's why it's called general, and when the other one's called special, right? We may say that according to the general theory of relativity, space is endowed with physical qualities. So he says space is physical. That's what Einstein was saying in 1920. In this sense, therefore, there exists an ether. So he's saying that space is filled with ether. There is all these bunch of particles in there. Some say it's moving, some say it's static. They have all these versions, right? But ether is a bunch of particles. That's all it is. Many particles. And just in case, many particles does not an object make. Okay? A tree is an object. Okay? A child is an object. Forest is not an object. Okay? Forest is many trees. Children is many many childs. Okay? So according to the general theory of relativity, space without an ether is unthinkable. Okay? So yeah, Einstein did not get rid of the ether. What he contributed was his name. That's all he did. He put his name on special relativity, took the credit for all of it. Okay, and what is interesting is that, you know, he eventually ended up in Princeton at the advanced studies there in Princeton. That's where he worked the last few years of his life. And here he confesses what happened in the last 6 years of his life, 6, 7 years of his life. And what did he conclude? He concluded he knows nothing, that he's an ignorant individual, that his life was wasted. Okay, and this is what Einstein says. Okay, he says, I'm generally regarded as a sort of petrified object, rendered blind and deaf by the years. People were laughing at him because he did not believe in quantum, specifically. I have become an obstinate heretic in the eyes of my colleagues. And then he says, all these 50 years of conscious brooding have brought me no nearer to the answer to the question, what are light quanta? Nowadays, every Tom, Dick, and Harry thinks he knows it, but he is mistaken. I consider it quite possible that physics cannot be based on the field concept. What did Einstein come up with? The field equation, right? In other words, on continuous structures. In that case, nothing remains of my entire castle in the air, gravitation theory included, and of the rest of modern physics. Yeah, Einstein died an ignorant man. He died disillusioned. He could never figure out how this universe works at all. And so he became an atheist in his own religion. Here's the pastor, here's the Pope of general relativity and special relativity. He took the credit for that as well. And turns out he dies saying, you know, I became an atheist in my own religion. I don't believe in it. That's how messed up all the mathematicians that picked up on what Einstein, the foundations he laid. They picked up on that, distorted it so much that Einstein said, you guys are all crazy. And so they said, well, you're too old. They didn't say he was crazy, they just said he was old. And so it's interesting that you have people like Don Lincoln who worship. In fact, everybody out there worships Einstein. Here we have another YouTuber who tries to worship and raise the value of Einstein, you know, to her Pope, her hero, okay? And this is Feathers, okay? And she's got this little Einstein there. It says, I'm all shook up. Well, we need Elvis here to put some music behind that, okay? So yeah, Einstein died an ignorant man. He never discovered anything. He didn't, all he did was mislead a generation, full 100 years of it, of mathematicians, down the wrong path. That's all Einstein contributed to so-called science, to physics. In other words, nothing. You could say he contributed negative knowledge, negative information, negative explanations, because all the explanations we have today from mathematical physics for all invisible, intangible objects out there that mediate, you know, how these phenomena work, is all irrational. Not one, okay, out of mathematical physics passes the rationality test. Okay, so let's move on to the subject matter of today. Let's see if we can find out what it is. Okay, give me a second here. Clean some of this up. Got a lot of stuff here. Okay, so here we go. Today we're going to be talking about gravity. What is gravity? And I always do an experiment. You saw it here for the first time ever. Okay, nobody else on planet Earth has ever done this experiment. Very expensive. Okay, we take a pencil. Okay, watch carefully because this is astounding. And you let go of it, and it falls to the floor, to the table in this case. And just in case, I'll do it repeatable because it's got to be repeatable in mathematics for it to be scientific. So we let go of it. Here it goes. There you go. See, you let go of it, falls to the floor. Never has it fallen to the ceiling whenever I do it. Okay, and so the question is, what brings it down? Why does it come down? What causes it? What's the mechanism? Okay, what comes in contact with the pencil? What physical object called? I mean, I'm holding it. So when I hold it with my fingers, yeah, it stays there. But as soon as I let go of it, it comes down. No way you can stop it. And so the question is, why does it go up? I mean, I want it to go up sometime, and it doesn't. Never been able to do that magic trick. Okay. So what's the deal? Well, here's a couple people. Several really. I've got 3 cases here where people have shown that when you drop it, it falls to the ground, but then you have, this inertia, this resistance that we talked about a minute ago, okay? Like the air, if you take a feather and you let go of it and, it doesn't fall like a stone does. It kind of floats there. Why? Because it's got this resistance. There's inertia, I guess, right? A little bit of inertia, a little bit of resistance, okay? And so the feather doesn't fall at the same rate, at the same acceleration as a stone. And here you have one fellow, his name is Brian Greene, and he went to a special place to do this experiment. They dropped a feather and a ball, and they both fell at the same time. Why? Because that chamber, they removed all the air. Okay, and so you can see there's no resistance, and it's uncanny. It's really unbelievable that a feather would fall at the same rate as anything else instead of floating. And all they did was remove the air. And here's another example of that. Okay, a fellow did the same thing. He had 2 boxes. In one he removed the air, in other ones he left it. And you can see the one with air, what the feather does. It kind of drifts because it's got all this resistance with the air, and the other one where there's no air just falls at the same rate as the little metal piece there, okay? And just in case, for those of you who are not flat earthers, we did it on the moon as well. An astronaut dropped a feather and a hammer, and you can see that they fall at the same time, okay? So he did it as careful as he could, okay? And there it is. No air on the moon, okay? So he proved that there's no air on the moon, right? And without that resistance, the feather falls at the same rate as the hammer. Okay, so we call that phenomena gravity. They both fall down. You can see that even on the moon, for those of you who are not flat earthers, the hammer and the feather did not go out into space. They both fell to the center of the moon in that direction, right? Okay, because the moon is round. Again, not for flat earthers. Flat earthers think the moon is flat, I guess, right? Okay, so what is this gravity thingy that pulls it down? Here's a definition. Okay, one's from dictionary.com, the other one from Wikipedia, and one says, gravity, the force of attraction by which terrestrial bodies tend to fall toward the center of the earth. Okay, that's the notion. What is it? It's a force of attraction, essentially, right? And Wikipedia says a fundamental interaction which causes mutual attraction between all things with mass or energy. Okay, so you have a mutual attraction and you have the force of attraction or fundamental interaction, right? The question is, you have an attraction. So gravity is not repulsive, okay? So whatever you let go of, it falls to the ground. unless there is some resistance, and then we have to go into inertia. But if there is no resistance, it'll just, or the resistance is irrelevant, like in the case of a stone, then the thing will fall at the rate that it should be falling, which is 9.8 meters per second squared. That's the acceleration of gravity here on Earth, and that's how fast, or how, the acceleration of gravity here. That's how you can expect the thing to fall to the ground at that rate. Okay, so gravity is some kind of force. That's a concept. So far we haven't said what gravity is. All we're saying is, look, we're going to call that phenomena gravity. Okay, and what is gravity? Gravity means that something falls to the floor. Essentially, there's a attraction. There's what is it? You could say it's attracted by the Earth somehow. Okay, magically, whatever, but it's attracted. And here's NASA. Okay, this is their version. It says gravity is a force. Okay, and again goes the same thing as the other two. And then it says, why do you land on the ground when you jump up instead of floating off into space? Yeah, why? And it says, why do things fall down when you throw them up or drop them? Okay, why? Yeah, I want to know why. The answer is gravity. Gravity is just a name. You could have said the answer is intelligence. The answer is love. I mean, love is attractive, usually, right? So, okay, so it's love. And what do you mean by that? I mean, did love cause, I mean, we're talking physics here, right? Did love bring it down? What's the physical mechanism? And, of course, no one even remotely has any idea. Okay, all these mathematicians, they never discovered that. Here we are 2,000 plus years later, since the Greeks dealt with some of these issues. Nobody has figured it out there in mathematical physics. Okay? We have, but not them. Okay, so here we have a fellow jumping on the moon, on the Earth. Okay, and you can see he tries to jump, but he doesn't go out into space. He falls back to Earth. Okay, and so what they've concocted is they said, well, the ether maybe, or who knows what, and we have all these particles, right? And they think it's a question of particles. Okay, and so they try to explain it with particles, but see, the problem is with particles coming out of objects such as atoms, right? They can only go one way. So assuming, there are particles coming out of your body, out of every atom in your body, right? Photons, for example, right? And then you have all these particles, we'll assume that they exist, right? And all these particles are coming from every direction. They're coming even from the atoms on the Earth. So why would you fall towards the center of the Earth? Why not? I mean, if you're in the middle of all these particles coming from every direction, you shouldn't move anywhere. Okay? If you jump, you should stay up in the air. Why do you come down? You can't explain it with particles. And someone who simulated these things with particles was Newton, but he gave up. He wrote a couple things that we have from him today. One is a letter to Richard Bentley, and he says that gravity should be essential to matter, so that one body may act upon another at a distance through a vacuum without the mediation of anything else, by and through which their action and force may be conveyed from one to another, is to me so great an absurdity that I believe no man who has competent faculty of thinking can ever fall into it. Okay? And so he says gravity must be caused by an agent. Yeah. And then in his book he says, I do not feign hypothesis. Okay, he had no idea, but he simulated everything with particles because he had no other idea what to simulate that with. Okay, but he was under the idea that, yeah, gravity must be caused by an agent. But it turns out that he can't see or touch whatever this agent is. Things simply fall to the floor, and I can't see or touch what's pushing or pulling them downwards. Okay, so he finally gave up. He says, I feign no hypothesis. Okay, but he did everything with particles. He was a particle man, corpuscles. Okay. So today, the people in quantum mechanics, they haven't given up on particles because their religion is a quantum based on the quantum, on the particle. Okay, particle that ain't a particle, by the way. It's an amount, quantity. It's a number, but they treat it as a ball. Okay, whenever they want to give their physical interpretation. Okay, and so here you have a couple instances. Okay, here's quantum attraction. Um, they call it transfer of negative momentum. And here's just an example of a quark shooting a gluon outwards and somehow drawing another quark inwards, you know? And here you have another fellow, and his name is John Baez, Juanito Baez, I call him. Says, if I throw a ball at you, the recoil pushes me back. He says, the answer, and he's trying to explain, he says, the answer lies in the Heisenberg's uncertainty principle. The photon can be created by one particle and absorbed by the other. If the momentum transferred by the wave points in the direction from the receiving particle to the emitting one, the effect is that of an attractive force. Here it goes again, just in case. If I throw a ball at you, the recoil pushes me back. When you catch the ball, you are pushed away from me. How can this attract us to each other? Yeah, good question. The answer lies in the Heisenberg's uncertainty principle. The photon can be created by one particle and absorbed by the other. Okay, so that's what he's saying. It's absorbed. If the moment transferred by the wave points in the direction from the receiving particle to the emitting one, the effect is an attractive force. Okay, so you can see how they're doing all this magic. They can do it mathematically. They say, yeah, we just change the sign or whatever. And yeah, that's great. That's got nothing to do with physics. Show me in a lab how you can do that. Okay, you like experiments? There, that's where you have to do experiments. Just show me an experiment where you show gravity, right, with negative momentum. Okay, just simulate. Throw a tennis ball at something and attract it. Okay. And here's another fella. His name is Victor Stenger. And give me a second here so we get to the beginning. The vacuum is capable of producing interactions between particles at effective space-like separation. This occurs when quantum fluctuations in the vacuum cause a particle to zigzag. Let me explain. No doubt the idea of motion backward in time makes a grievous assault on common sense. Yeah. However, to a particle physicist raised on a diet of Feynman diagrams, motion backward in time is not all that disturbing. All fundamental particle interactions work backward as well as forward. And so these people believe that they can get away with saying, look, we just changed time. We put a negative sign in front of the little t, and we've got it made. Okay? So these folks are really saying that, you know, they can produce attraction by throwing something outwards one way. Okay? They have no problem believing this. And the question is, how do they justify it rationally? And they can't. They just say, you know, again, like this fellow says, you can't even imagine that. How do you throw the ball and attract? And so they had to create negative momentum transfer. And that answered, I guess, Newton's concern. You know, how do you produce attraction with particles? And these people said, we can do it. We just caught negative momentum transfer. We transfer attraction. Okay. Okay, so what is that particle called? It's called the graviton. Okay, and what is a graviton? Well, here you have an idea. It says the graviton is the hypothetical quantum of gravity, an elementary particle that mediates the force of gravitational interaction. This is all out of the Wikipedia. There is no complete quantum field theory of gravitons due to an outstanding mathematical problem with renormalization in general relativity. Okay, in string theory, okay, so they moved from quantum to string theory now, which is a variation on quantum. That's all it is. One of the vibrational states of the string gives rise to the graviton. Okay, so they're just saying that it's a little string that's vibrating. It's more like you know, like this. More like something like this, and they move it around in different directions. They say, well, that's a particle. Okay, great. And so it says, one vibrational states of the string gives the rise to graviton, a quantum mechanical particle that carries gravitational force, carries it on the back, okay? They always talk about carrying force, carrying interactions. How you do that, I don't know. And we don't carry concepts in science. Thus, string theory is a theory of quantum gravity. Okay, you got that? It's a theory of quantum gravity. In string theory, the graviton is a massless state of a fundamental string. If a massless spin 2 particle is discovered, it must be the graviton. So here you have a picture of that, okay? This is what a graviton looks like, okay? So if you see something like that around your house, floating around, hey, call the people at CERN, SLAC, Fermilab, you know, any of those. Brookhaven, National Laboratories, any of those. Tell them that you've seen a graviton, okay? It looks something like that. So now you know what it looks like, no excuses, okay? Okay, so if you see something floating like that, it's not a unidentified flying object, it's a graviton, okay? Okay, so here we have one fellow. His name is Matt Dowd. He's got, again, he's sponsored by PBS. I call it BS more than PBS, okay? And this is what he says. He says, dozens of these cosmic strings in a network across the universe. Okay, so all these strings somehow open up, they break, and then they weld together or sew together. He doesn't explain the process. He doesn't explain how that happens. They just do it. They just describe and illustrate that the string, this closed loop string, this closed loop rubber band or string or whatever, it breaks, forms welds or whatever with other strings, and then they form these loops again, then they break again, and they do all this stuff, and nobody tells us how that happens, okay? And what Matt does, he goes in there and he says the following. He says, a pair of kinks in the string are whipped back and forth by the oscillating string, okay? We see it there, okay? And the incredible mass in these kinks, they have incredible mass, okay? No, I don't know how they justify that. They just say it does. Causes them to radiate gravitational waves. And so they slowly decay away. Gravitational waves. I guess he's talking about space-time, right? These waves are going to travel through space-time because these massive strings, they vibrate and all these waves come out of there. Fine, no problem. How does that wave that comes towards me attract me? That's what I want them to tell me. Because a wave, like a particle, is a one-way mechanism. It goes outwards and does not come in. Okay, so we have a problem because these people do not explain the mechanism. All they say, look, it does so. Okay, so the wave comes out of the string, the closed loop string. It vibrates, creates waves in space-time, I guess, goes outwards, no problem. And here I'm on the receiving end. So we have waves coming towards me, like, in the ocean, when the waves come towards you. Well, the wave is not pulling you in, it's pushing you out. You could say that, later on, it pulls you inwards, okay? But that's not what these people are saying. These people are not saying, besides, it's not going to pull you all, even if you're pulled by the wave, you're not going to be dragged all the way to the black hole, okay? So what is the pull mechanism? Because, again, gravity is an attractive force. Explain attraction with this wave or your particles, either way, okay? And that's where they can't. They don't have that. Okay, but it says that the string disappears. Disappears into what? It becomes part of space-time. I mean, here you have this string, right? This thing, right? It's vibrating. It sends waves out. And because it loses all this energy in the waving motion, this disappears. Where does it go? I mean, does it melt away? Does it become part of space-time? Was it a thing to begin with? I mean, is it a wave? What is this one-dimensional string? I mean, I don't know anything that's one-dimensional. I mean, what does one-dimensional look like? And they say it only has length. So, draw it for me. Draw your one-dimensional length, okay? And fortunately, someone here, his name is Brian Cox, he tells us where these gravitons go, why they disappear, why we can't see them. Okay, this is important here, so pay attention. And he says the following, he says that it goes to hidden dementia. Okay, you have dimension is one, dementia I guess is many, right? The reason gravitons disappear is that they vanish into a place beyond our reality. into some sort of extra dimension. Okay, great. How many drinks did you have? There can be extra hidden, unseen dimensions. Okay, great. It sounds ridiculous. Absolutely. That's why I asked how many drinks you had. Bartender, I want whatever he had. And it is impossible to picture, but theoretically it's possible. I mean, these people are so gullible, they believe anything that their teachers tell them, and they just memorize it for the test and then spread it out among humanity, right? And it's also possible that gravitons, the particles of gravity, can spend most of their time in those extra dimensions. So, yeah, if you're looking for a graviton, go to the other dimension, you'll find it there. Okay, that's what they're saying. They're hiding in the extra dimension. Okay, and so that's the quantum string version, right? Here you have Einstein's version. We covered that the other day. It's very simple, so we don't need to spend more time on this. The Earth doesn't fly out of the solar system because there's this canvas known as warp time. Okay, we have the seconds and the minutes, which are warped, or the years maybe, right? And they're warped, and they come up against the skin of our planet and prevent our planet from flying out of the solar system. That's what keeps our ball rolling around the sun. Okay, and so what can I say? These are the versions that you get. These are the explanations, the mechanisms that they offer you in mathematical physics. And so if you believe any of them, well, I don't know. I think you need to see a doctor, called a shrink. Okay? Well, how do we explain it? Well, obviously we explain it very simple because it is very simple. All we needed to do here, okay, when we had the pencil, right? All we needed to do here is figure out what invisible thing, object, entity, whatever you want to call it, body, is here or here. Something that comes in contact with a pencil. If it comes in contact with a pencil, we can explain why it falls, because there is no action at a distance. There is something in contact with a pencil, physical contact with a pencil other than the air, right? There's something invisible, intangible, that's coming in contact with a pencil. Okay? If you say there ain't, you say that there is nothing that's in contact with a pencil because we cannot see it or touch it, you are explaining this phenomenon with black magic. You're saying this happens by magic, with nothing touching it, nothing coming in contact with it. When you jump and you fall back to earth, why do you fall back to earth? Well, nothing is in contact with me. Yes, something had better be in contact with you, otherwise you are explaining your phenomenon, the fact that you jump and you're pulled right back, you're explaining that with black magic. Okay? So before we explain our version, let's give an introduction to it. You have to know what we're trying to figure out here. Okay? And this is a very important thing that a professor, his name is Richard Muller, he worked at least at Berkeley, okay, and this is what he had to say about what it is that you have to explain about gravity. Okay, listen carefully. Okay, this is not mine. This is someone at Berkeley, professor, right? This is what he says. Okay, here goes. Listen carefully.
What's the force of gravity on me? It's the pull of the Earth on my body. So, for example, if you have the Earth with its big mass here, and you have you with your little mass here, that every atom on the Earth is pulling on every atom of you. You're also pulling on it. On the other hand, there are a lot of atoms here you're pulling on. You're pulling on all of them. The amazing thing about gravity is it goes right through things.
Okay? Every atom of you, every single atom in your body of you is pulling on every atom of Earth. Every atom of Earth is pulling on every atom of you. Okay? If you say there's nothing there because you cannot see or touch it, you're doing black magic. The only way you can pull on every atom on Earth and for every atom on Earth to pull on you is because there's an invisible, intangible thing, elongated thing that is connected from every atom in your body to every atom on Earth. There is no other explanation for that. And the only reason the mathematicians have not ever come up with that is because they could not see or touch it. But an object is not that which you can see or touch. An object is that which has shape. An elongated object has shape. 3D object, right? It has shape. It doesn't necessarily mean you can see or touch it. Okay, that's the bottom line. That's what prevented this from, or why it took more than 2,000 years to figure this out, because they could not see or touch it, and they said, we're going to resolve this through mathematics. No, you can't. And you can't resolve it through an experiment, because if you cannot see or touch it, you cannot go to the lab and say, I'm going to see or touch whatever is mediating gravity. You can't, because you can't see or touch it. Is that clear? And this is what these people never figured out, because they're trying to do math. They're just saying, well, this is the force of attraction. Yeah, that doesn't tell me what caused it, the mechanism. Okay, that's the issue. Okay, so we got that straight. That's what we have to explain. And here we have it. This is the difference between mathematical physics, that's been done until today. They're talking about discrete particles. That's why they cannot explain anything. That's why they talk about action at a distance. Under the proposal that we have here is we say that all atoms are interconnected. Now you can explain why every atom on Earth pulls on every atom of you, and you pull on it, because every atom in your body is connected to physically connected to every atom on Earth. It's connected via an intangible, invisible entity. We call it the rope, because that's the shape it has, and that's the only reason for that. But it's an elongated, very skinny, very thin object that we cannot see or touch. We pass our hands right through it. Okay, and that's why every atom of you pulls on every atom of Earth. Every atom on Earth pulls on every atom of you, which is what we have to explain. And here we explain it. We're saying every atom in your body is connected to every atom on Earth. We're done. That's how simple it was. No mass, no energy, no field, no force, none of those mathematical words, just physics. We're saying your atom is attached to the atoms on Earth. Every atom in your body is attached to every atom of me, okay? And so on. All atoms in the universe are physically interconnected. No action at a distance, no black magic. Once you have the connection, it's easy to understand. It's kid stuff, okay? And I always give the example, guy brings his 10-year-old son, and they see a farmer pulling on a donkey from a rope, right, tied around the donkey's neck. So as he pulls, the donkey comes towards him. So the man asks his son, how did he get the donkey from point A to point B, closer to the farmer? And the kid says, he pulled on the rope. It's so simple. It's just not even, it's a no-brainer. It's what you saw him pulling on the rope, pulling on the donkey. Now make the rope disappear. And now the farmer goes like that, and the donkey comes towards him. And now the father asks his son, how did the donkey go from point A to point B? And the kid says, I have no clue. I don't know how that happened. Magic. And the only issue is that he can't see the rope. Because if he could see the rope, it was kid stuff. But if you can't see the rope, it's black magic. We'll never answer the question. That's all it is. That's where we're at today. Okay, so here we have our explanation for gravity. Okay, here it is. We call them effective ropes. You have 5 atoms in the cube tied to one atom, number 6, in the cylinder. Okay, we call it one effective rope because essentially it's a pull or a tug between 1 and 6. 2, 3, 4, and 5 don't exist for all practical purposes because they're on the same axis. So they're all pulling on the same line, so to speak. But what happens when they go out of alignment? For example, when the distance between the cylinder and the cube change, cylinder comes closer. Well, now you can see that the atoms are the ropes that connect, or these effective, we call them effective ropes. Now each rope is pulling independently and not on the same axis. And so it's like suddenly you have 5 ropes, okay, instead of one. Okay, and that's why gravity increases as two objects come closer to each other. And there on the upper right, you'll see two objects far away. They have all the ropes more or less on the same axis. Lots of them are exactly on the same axis. They superimpose. And again, because there's no see or touch between ropes, okay, they don't touch each other. They superimpose perfectly well, okay? And that's what people have trouble understanding or accepting, okay? But that's an assumption you have to make. And then what happens as the objects come closer together? Well, the ropes fan out, and you can see how gravity is becoming stronger and stronger as the distance between the two objects decreases. Okay, so what is Newton's equation? Weight equals gravitational constant G, mass divided by distance squared. Well, what you're talking about is the number of effective ropes. That's what the mass divided by distance square factor represents. It in fact represents the number of effective ropes. Okay, that's our explanation. Okay, and so here we have a comparison. Okay, of the 3 proposals. Okay, here's the quantum slash um, string theory proposal. Okay, you have all these particles coming from the Earth to the Sun, or the Sun to the Earth, and somehow that prevents the Earth from flying out of the solar system. How do you produce that? By throwing particles one way. Okay? So whether the Earth throws particle at the Sun or the Sun at the Earth, it doesn't explain the mechanism. It doesn't explain gravity. It doesn't explain why the Earth doesn't go flying out of the solar system. Okay? So it doesn't. It's an irrational mechanism to introduce particles. Here's the relativity version, which is another one. Okay, here you have the Earth going around space-time. Space-time, the sun is in the center, blowing or pushing, I guess, the canvas downwards. And so because it pushes it downwards, it creates this depression in time. Okay, so we have warp time. That's what the green stuff represents. And now that you have that green warp time, the Earth that cannot fall out of the solar system, you could say, or fly out. Why? Because its surface is rolling or sliding around that warp time. What sense does that make? None at all whatsoever. So don't tell me you proved it. Tell me what the mechanism is. Tell me how you're going to warp time. What are you warping? The seconds, the minutes? And here's our version, okay, and you can see it here, very easy to understand. The sun simply twirls the Earth around itself, okay? And why? Because all atoms on Earth are connected to every single atom in the sun. The sun simply goes around and twirls the Earth around itself, okay? And that's easy to understand. Now you know why the Earth goes around the sun. There's no friction between the Earth and space, because space is absolutely nothing, meaning it's that which has no shape. So there is no friction between Earth and space. Earth cannot rub, Gaia cannot rub her shoulder or her elbow against space, because space is absolutely nothing, meaning that which has no shape. There is no ether in there. It's not filled with energy or fields or any of that nonsense. No, all we have is between objects, between atoms, you have these elongated entities. We'll call them ropes. Okay, and that's why celestial objects don't fly out, for example, out of the solar system. They swing around. And then, is there something out there in space? All we have is the crisscrossing of ropes from other atoms in the universe, going right through the Earth and out to other atoms on the other side of the universe. That we have across the entire universe. People say, how many ropes are there? We don't care. There's lots of them. There's lots of atoms in the universe. There's lots of ropes. Very simple stuff. No biggie. Okay. Quantity is not an issue. Okay. So those people who raise quantity issues are simply chasing their tail around. Okay, let's get down to the questions. We're not going to do our science guy today. We finished the other day. Essentially, we said everything we had to say, I guess, about predictions. Okay, so there's nothing more to add. Essentially, he has a different version of the scientific method. That's the one they shoved up his nose holes, in high school or college or whatever, and that's what he believes. That's what he's been educated on, brainwashed on, hypnotized on, and all he does is repeat it. He doesn't try to make sense of any of that. Okay. Okay, so here we have it. Fellow says, I used math to create angels. Does this mean angels exist? He was answering another fellow there, and it's a good question. The fact that you can mathematically say, look, I created space-time in my math. I've got all these coordinates. Does that mean there's a physical object called space-time out there? Okay, the fact that you can do it mathematically. Okay, and here's an example. Okay, here we have the Earth going around the sun. Okay, and okay, we've seen that. We all recognize that. No biggie. But what if I told you, look, that angels exist? So here you have the angel taking the Earth around the sun. How's that for an explanation? Could that be true? Okay. And I'm saying that just because you can conceptualize angels, you cannot come up with a theory and say, well, angels push the Earth around the sun. And likewise, it makes no sense to say that, general relativity, space-time, is the one that's going to prevent the Earth from flying out of the solar system. Is space-time a physical object? Is there such an entity, such as space-time? And the answer, hopefully, is no. Okay. Okay, so let's get these fellows out of here. Another fellow says, there are 100+ theories of ether. Okay, your rope theory is just another ether theory. Well, first of all, rope is not a theory, it's a hypothesis. It's an assumption. You make an assumption, which is not a theory, okay? You make an assumption, say, let us assume that every atom in the universe is connected to all others by means of a rope or some elongated object. Could be a line or whatever, I don't know. You can propose whatever you want. It's an assumption, not a theory. Okay, so far we haven't explained anything. All we did was propose an assumption. The guy says the rope theory, so he's already started on the wrong shoe. Okay, but what's the issue? He says there's a bunch of ether theories out there. Again, the ether is an assumption. Okay, it's not a theory in itself. And you look up the word ether, and I challenge anyone out there to do so because nobody can tell me what the ether is. Everybody tells me I'm wrong, that I don't know what the ether is. Fine, no problem. I'll accept that. Tell me what the ether is. Is the ether a physical object? Draw it, illustrate it, point to it somewhere on the internet. And if it's a concept, define it. Tell me what you think the word ether is, what it represents. What is the ether to you? Don't tell me I'm wrong. Tell me what's right. Okay? And here you have it. If you look up the word ether in the images, right? I Googled that, and that's what you get. Okay? So apparently nobody has any idea what the ether is out there, especially all those people who propose the ether. In fact, one fellow there, Jeff Yee, where you see up at the top, what is ether? It's a YouTube video, and he goes in there and he believes in the ether. Okay, tells you why. But he says, what is the ether? And what is ether? And he never tells you what the ether is. Okay, he doesn't tell you what it is. He says it's a substance that fills space. You haven't told me anything. That's not what the ether is. Point to it. If it's a what, if it's a thing, point to it, draw it, illustrate it. And again, they can't illustrate the ether. They just tell you that you don't know what the ether is. I know, but you don't. Okay, I don't. I'm ignorant. I don't know what ether is. Tell me what it is. Is it a thing? Illustrate it. If it's a concept, define it. Once again, okay? Okay, so since they don't, I do. I do illustrate the ether, and you can't illustrate it because it's a bunch of particles. That's why you can't illustrate the ether. Okay? You're saying you just illustrated, Bill. No, because a bunch of particles does not an object make. Shape is what characterizes an object. And right now, it doesn't have shape. I put a frame around it because I didn't want to have an infinite object, right? Meaning infinity of particles. So I put the frame around that just to show you what all these people have thought about the ether for centuries, okay? And what they say is that the ether is, in other words, light is the vibration of the ether. And this is what they illustrate. Okay, this is what they have in mind. They're saying, look, all these particles are vibrating, and that's what light is. It's the vibration of these gazillions of particles. Okay, so that's what the ether is. So if you don't believe that, if you don't like that, you don't say you don't agree with this definition, this notion, then tell us what the ether is. If it's if it's a what, then illustrate it. Okay, you can't just say you don't know what it is. No, I don't know what it is. I want you to tell us what it is. Okay, it's the ball is in your court if you're going to vouch for the ether. Okay, so let's get it right. Okay, so is my theory an ether theory? Well, this is what I propose. Now, does that look like the bunch of particles you just saw? Okay, so I guess not. This is a little different. The black stuff is space, and I put a ring around it, but actually, space is not finite or infinite. Space is a concept. It's a synonym of nothing. What is nothing? That which has no shape. What is something? That which has shape. Okay, so the thread that you see there, I made it kind of fat, kind of thick, okay? But you can think of it as very thin, extremely thin, and that's all there is in the universe. And what does this thread do? Well, this thread converts into everything that we see. You have the single closed loop thread. It's twined around, more twined, and eventually it ends up being atoms and the interconnections that that connect every atom in the universe. Okay, interconnected atoms. Okay, that's the assumption. That's what we're saying exists out there. That's all that we have in our universe. It's a very simple universe. It's just atoms connected to each other. That's all there is. And if we were to untie every atom, every rope that connects any two atoms, we would end up with a single closed loop thread in the universe. Okay, so that's the proposal. And from there, we can explain gravity, and we can explain light, we can explain all the main phenomena, the basic phenomena of physics. Okay, no magic, it's just that we can't see or touch the mediators. What are the mediators? The mediators are the ropes. And eventually, if you untangle all that mess that we've got out there from atoms to the ropes that interconnect them, you end up with a single closed loop thread. Okay, that's the way it works. Very simple universe. None of this math nonsense. Will we ever figure out? We'll never figure it out. Yeah, we figured it out already. Okay, we have an explanation. You don't like our explanation? Come with a better mousetrap. That's the way it works. Okay, so you got a better explanation. Better be rational. That's all we ask. Okay, fellow says your question about physical mechanism are meaningless because the empirical reality around us just is. So he says, I just believe it. I just accept it. I don't need to know the mechanisms. Yeah, because he's not a physicist. Physicist wants to know mechanism. We want to know why this thing falls to the floor. Okay? Why does it fall down? And he says, it just is. But yeah, you haven't explained it with that. So he just accepted it. You could just say angels and he'll accept it as well and say God did it and it's all the same to him. Okay? We don't question the mundane reality around for some hidden mechanisms because we just accept it. And then these people, why are these people coming into physics? These people should be in church praying for their salvation, for reincarnation or whatever. That's how you should feel about relativity. It just is a truth about our world. A truth. That's truth. Okay, it's just no mechanism or irrational mechanism, but it's just the truth. Okay, truth means he accepted it. They shoved it down his throat. He swallowed it. Okay, Kool-Aid. Physics is about measurement. So we measure and we just accept it, and that's it. Even Einstein can't believe what this guy said. Yeah, Einstein tried to get to the bottom of it. He never did. He never figured it out. Died an ignorant man. Okay, and another person says a shadow seems like it exists and does, but not as a thing. Well, then it can't exist because exist requires it to be a thing, an object, a entity, whatever synonym you want to put in there. Okay, with properties of its own. Rather, it is an absence of a thing, like light. Yeah, if it's an absence of a thing, if it's light, meaning vibration, we're talking about the vibration of light of the rope. The rope is a thing, but the vibration is not a thing. It's what the rope does. Okay, so we have to distinguish when we use the word light between the object and what it does. Okay, the noun and the verb. Okay, and so yeah, you need a thing, and what the problem is, it's got to be a standalone thing. Shadow is not a thing. You say, well, it's got shape, not for the purposes of physics. Shape means standalone. Okay, if it doesn't stand alone, if it needs help, like the halo on the head of an angel, without the angel, that's just a plate or a ring. It becomes the word halo only if you put the angel, the holy person there. Okay, a halo is not a thing. Okay, halo is a concept. Okay, because it's a relation. Without the angel, all you have is a plate. Now you have an object or a ring, right? Those two are objects. With the angel, it becomes a ring, a halo. Now it's not an object. Halo is a concept. And it takes 10 years for mathematicians to understand what I just said. Okay, folks, then we'll stop here and we'll see you next week. Same time, same